guys. So today we're going to be putting our focus onto the law of conservation of mass. Before we get to the actual words of the law, we do need to talk a little bit about this. So we've already been working on chemical formulas where we understand that the element symbol and subscripts determine what elements and how many atoms of each element occur inside of a molecule or a compound or both. So, um, just like a chemical formula is a short way to represent a molecule or a compound, a chemical equation, like you see here, is a short way to represent a chemical reaction. So, like I've said before, everything in the universe is made up of the 118 elements on the periodic table. But there are way more, exponentially more things in the world than just 118 things. So the elements on the periodic table have to combine to form all of these substances that exist in the universe. Everything is made of chemicals. You're made of chemicals. Your clothes are made of chemicals. Your deodorant, your perfume, your cologne, the food that we eat, the cars that we drive, everything is made up of chemicals, and we can break those things down to their smallest parts, which are atoms. So, what a chemical equation shows us is kind of a recipe to make all of these different substances. So, for example, what you see here, very simple, a molecule of water, H2O, okay, comes from the combination of hydrogen and oxygen. So when we look at an equation, the left side of the equation are called the reactants. So this is what goes in. So this is the individual ingredients, just like if you were baking a cake, it would be the eggs, the flour, the sugar. These are the individual ingredients that go into making what we call the products. So the reactants are what goes in, okay, and the products is what is created afterwards. The part that divides those two sections, that arrow, is called the yield sign. So it's very similar in math to an equal sign. So now you'll see on the next slide that some equations, like the one that we just saw earlier, look like this, right? This is A plus B, so this would be H2 plus O2 gives us some combination. We call that a synthesis reaction because something new is synthesized from two different things. But that reaction can also be a decomposition reaction where you have one thing and it gets broken down into its component parts, A and B. There's also what we call the single replacement reaction. And I usually kind of compare this to A and B are on a date and C is at the same place but by themselves. And then when all is said and done, A and B break up and A and C get together and then B goes home alone. So that's called a single replacement. The double replacement reaction is when you have this pair A and B, and you have this pair C and D, and then the resulting product is they basically just flip flop. So C went from being bonded with D to being bonded with A, and B went from being bonded with A to being bonded with B. So those are the four different types of chemical reactions. So here is the same thing. It's a chemical reaction written two ways. One way is with the chemical formulas, and another way here is with the models of the atoms. So this reaction here is the combustion, which is basically setting on fire of methane. Okay. So if we add oxygen to methane and combust it, meaning add energy to it, then you'll notice that these four hydrogen atoms that are surrounding carbon break off, and these two oxygen molecules here break apart. Two of those oxygens end up with the black carbon right here to form carbon dioxide, and the other two oxygens hook up with these four hydrogens to form two molecules of H2O. So again, this is where we talked earlier about making sure we understand how to recognize chemical formulas and then also how to model what's actually happening. And a lot of times the model actually helps us understand things better than just seeing it written out like we have here. Okay? All right. So now with that brief introduction to chemical equations, and we'll do some more work with those later on, the law of conservation of mass. Okay, so in a chemical reaction, matter or mass, same thing, because all matter is made of mass, is neither created or destroyed. It only changes form. So, in other words, more simply put, what we start with, we have to end with. Now, we're not saying that what the substances that we start with, we have to end with. What we're saying is the ingredients to the substances that we start with, we have to end with. Okay, so we're not starting with water and ending with water. We may be starting with H2 and O2 and they become water, or we may start with water and it becomes H2 and O2 and decomposes into those two separate things. But ultimately, what you need to understand is however many atoms you have on the left side, you have to have the same number of atoms on the right. So atoms can't come from nowhere. So when we're writing chemical reactions, we have to make sure that they are what we call balanced, meaning that the same number of atoms are on the left side that are on the right side. So during a chemical reaction, chemical bonds are broken and atoms rearrange to form new substances like we saw on the slide before. And these reactions can require energy to be put in, okay, or they can release energy. So the two words that we use for that are endothermic if it requires energy, and exothermic if it lets energy out. So if a reaction gets hot, energy is being released. That's an exothermic reaction. So digestion in the human body would be an example of exothermic because it gives off heat, and that's what basically generates our body heat is the process of digestion. Other reactions can get cold, and those are reactions that are requiring energy to be put into the system, and then they get cold on the outside. So you can go buy an ice pack, let's say from CVS or Walgreens, and if you break it and shake it up, it gets cold. And so when the two chemicals mix, they're actually absorbing energy, which makes it feel cold to the outside. And that's an endothermic reaction. So here's that same reaction that I showed you before. So again, if you look on the left side, we have one C, one carbon on the left, one carbon on the right. Okay, so we need to make sure that the number of atoms that we have on the left side, the left of the arrow, is equal to the number of atoms we have on the right side. Okay, so excuse me. So if we break this down, we have one carbon here and one carbon here. We have one, two, three, four hydrogens. Over here, we have one, two, three, four hydrogens. We have one, two, three, four total oxygens. And over here, we have one, two, three, four total oxygens as well. So this follows the law of conservation of mass. What we started with, the numbers of atoms that we started with, we ended with. Sometimes, however, when chemical equations are written, they're not written correctly, and we have to recognize when they're not. We don't have to know how to fix them yet. That's a high school thing. But as an eighth grader, you do need to know how to recognize whether or not an equation is balanced or is not. So not only do the number of atoms have to match on the left and the right, the mass of what's on the left also has to match the mass of what's on the right. So this is the same reaction, just kind of written out in scribble. We started with the CH4 and 2 oxygen molecules, and there were 16 grams of methane and 64 grams of oxygen, for a total on the left-hand side of the arrow of 80 grams. So the right side also has to have the same, not only the same atoms, but it also has to have the same mass, because this is the law of conservation of mass. Mass is not created or destroyed. So the mass of the reactants has to equal the mass of the products. So you may get a question that looks like this. If we have 80 grams to start with, and we have 80 grams to finish with, and 44 of those grams are taken up with carbon dioxide, then how many grams of water do we have? And so because this has to equal 80 over here, 44 of them are taken up with carbon dioxide. The other 36 grams have to be water, because the right side has to equal the left side. So again, not only do you have to match up the atoms on the left and the right, you also have to add up or match up the masses on the left and the right. So that's basically, in a nutshell, what the law of conservation of mass is. Okay, so let's kind of do a little bit of practice. So let's look at this equation here, and we have to determine whether or not this equation follows the law of conservation of mass. So there's kind of a step-by-step process. You may be able to just immediately recognize whether it does or whether it doesn't. Okay, but I'm going to kind of show you how to go through a step-by-step process, because not all of the equations that you're going to see are going to be this simple. So first step is to split the equation in half and count the atoms on both sides of the equation. Step 2 then are the types and numbers of atoms on the left the same as the types and numbers on the right? If they are, then it follows the law. If they aren't, it breaks the law, and then we have to try to fix it. Now, again, we're not going to ask you to fix it this year in 8th grade. Okay. All we are asking you to do is determine whether it does or whether it doesn't follow the law of conservation of mass. So here it is, step by step. So on the left-hand side, again, we have the reactants, 1 molecule of H2, 1 molecule of O2, and over here, the products, we have 1 molecule of H2O. So again, taking this step by step, the first thing we want to do is split the equation in half with a line, dotted line or solid line, doesn't really matter. And we want to list the elements that we see on the left-hand side. And so the 2 elements that we see over there are hydrogen, H, and oxygen, O. And then we need to count how many atoms of hydrogen and oxygen that we have. So the subscript here tells us that there are 2 atoms of hydrogen. And this subscript here tells us that there are the model there's 2 atoms of hydrogen down here, sorry. And then there are 2 atoms of oxygen. So what's happening is we're taking this molecule of hydrogen and this molecule of oxygen, and we're combining them. Okay. Now let's go ahead and look on the right side. On the right side, we have hydrogen and oxygen. So the types of atoms are the same. So now we have to figure out if the numbers are the same. So in this formula here, the 2 tells us that there are 2 hydrogens, and the lack of a subscript here tells us that there's only 1 oxygen. So looking at these numbers and looking at these numbers, we would say that this does not follow the law of conservation of mass. Okay. So we're missing something over here that we started with. And remember, matter cannot be created or destroyed. It can only change form. So we're missing one of these oxygen atoms over here. So the only thing that we can do is put coefficients in front of these um, chemical formulas to change it. So just like in some recipes, something might need one egg, but in another recipe, you might need two. So we cannot change, we can't like take one of these away to make this just O, and we can't come over here and add a two right here because then it's no longer water. It becomes hydrogen peroxide. The only thing that we can do to change these numbers is add coefficients to the front of these. So the first thing you want to do is figure it out. I'm short of an oxygen here. So I need to get two oxygens here somehow. And the only way I can do that is I can't put a coefficient here. The only place I can put a coefficient is here. Okay. So now I have two molecules of water. So that would change my numbers of hydrogen to 4 and oxygen is now 2. So now over here, I have two molecules of H2O. So the one thing about understanding this is by solving the oxygen problem, we created a problem with the hydrogen. So now I have 4 hydrogen over here. So now I need to fix the hydrogen issue. So I can come over here and I can put a 2 in front of this hydrogen, which changed the numbers of hydrogen now to 4. So now my numbers add up or are equal to one another. 4 hydrogen on the left, 4 hydrogen on the right, 2 oxygen on the left, 2 oxygen on the right. And if you look here in the model, here are my 4 hydrogens, here are my 2 oxygens, and then over here, here are my 4 hydrogens, and here are my 2 oxygens. So now this formula follows the law. Okay. All right. So let's look at this one. So this is a reaction of photosynthesis, which you learned about in 7th grade. This is the process that plants go through to feed themselves, because that's why they're producers. So what the plants need over here on the reactant side is carbon dioxide from the air and water from the ground. And then in the chloroplast of the plant cell, the chloroplast is going to create this molecule, which is a molecule of glucose, which is a type of sugar. It was actually on your assignment that was due last night. And that is the correct order that it should be written in. And then there's O2. So as we should know, plants give off oxygen, right? So we're going to try to see whether or not this equation follows the law of conservation of mass. So best way to do that, I'm not going to list the elements, I'm just going to model it. So right here, I have one molecule of carbon dioxide. Here's my carbon, and these are my 2 oxygens. And then here I have one molecule of H2O. So these are my 2 hydrogens, and this is my 1 oxygen. So total, I have 3 total oxygens over here, and I have 2 hydrogens and only 1 carbon. So we could probably already guess that this is not going to follow the law of conservation of mass, because if you look at these subscripts here, they're pretty big. But let's go ahead and model it anyway. So this is what my version, it doesn't actually look like that, but this is just a simplified version of a molecule of glucose. 6 carbons, 1, 2, 3, 4, 5, 6. 12 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 6 oxygens, 1, 2, 3, 4, 5, 6. Now, we also have this one molecule of O2. So if you do the math, there are 8 atoms of oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 oxygens over here, but there's only 3 oxygens over here. So automatically we know that this does not follow the law of conservation of mass. Only 1 carbon on this side 6 carbons on this side, and 2 hydrogens and 12 hydrogens over here. So one of the first things we need to do is we need to figure out one element to fix, right? So if I've got 6 carbons over here, what number can I put over here to give me 6 carbons? Well, it's easy. I can just put a 6 there. Now, when I do that, I also kind of add some oxygens into the mix too, because 6 multiplies this to create 12 oxygens total. So now I have 6 carbons over here. I have 6 carbons over here, so my carbons are equal. So let's look at the other ones. Oxygen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm missing one right here. There it is. So there's 12 oxygens here, 1 oxygen here. Okay, so there's 13 oxygens over here. But if I add this here, now I can look at it and count up my oxygens. 1, 2, 3, 4, 5, 6, and then there's 12 over here for a total of 18 oxygens. My hydrogens are good now because there's 12 hydrogens over here. Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my carbons and hydrogens are now equal. But now I have to fix my oxygen problem. So over here, I have 18 total oxygens. Here I have 6. So 18 minus 6, I would need 12 oxygens over here to make this completely balanced. So what number can I put here that will multiply times this to give me 12 oxygens? So if I use a 6, 6 times 2 is 12. So now if I count everything up, I'll have 18 oxygens on the right, 18 oxygens on the left, 6 carbons on the left, 6 carbons on the right, 12 hydrogens on the left, 12 hydrogens on the right. Now, again, you don't need to know how to do that. Okay, that's a high school thing. All you will be able to do, all you will have to do is be able to look at the equation and determine whether or not it's balanced. So it's real simple. You just start with the first element that you see over here. And so if you only see one C, and then you come over here and you see 6 C's over here, immediately you know that this equation does not follow the law of conservation of mass, and you don't have to go any further. One thing that a lot of students do forget, though, is to forget that there may be oxygens in this formula and in this formula, just like there's oxygens here and here. So the total oxygens on the right here is 6 here and 2 here, so that would be 8. And the total oxygens on the left is 2 here and 1 here for a total of 3. So again, that's all really you're being asked to do, is to be able to recognize whether or not these equations are balanced. Okay? All right, guys. So that kind of sums it up. We'll practice this, of course, as we move forward. So I know it seems to be a lot. It may seem a little bit confusing, but it's really not as hard as it may seem. So just be patient. Go through each one of these problems that you're going to do step by step, and you'll be fine. All right, guys. Good luck.